Okay, now we're going to finish this section up with one complete example of the Gauss Quadrature three-point rule with a function that we saw a little bit earlier. So we're going to approximate this integral from point 1 to 1.3 of 5x e to the negative 2x dx by the three-point Gauss Quadrature Rule. I put our little cheat note up here, how to transform an integral from an arbitrary a to b into one that goes from -1 to 1 so that we can use the table in the book to find all of the nodes and the weights to use the three-point rule. Okay, so recall that the integral of a function from 1 to 0.3, converting it using this way, is simply b minus a over 2, as the formula says, times f of this dt. This was b minus a over 2t plus b plus a over 2. Now, maybe a little sloppy, I prefer x's over t's. From here to here, I changed the variable from t back to x. It's basically used as a dummy variable. So here is what we're looking for by using the three-point Gauss Quadrature Rule. That's equal to exactly what we're looking for. Well, not exactly, it's our approximation to this. Well, let me rephrase that. This is exactly this. We're going to use the Gauss three-point rule to approximate this, which means we're approximating that. So from table 5.1, I looked it up, and this is the information we get from table 5.1. We know that if it's a three-point rule, it looks like this: 3 coefficients, 3 x values, 3 nodes is what they call those. And it tells you in the table, C1 is this, C2 is this, C3 is this. X1 is this, X2 is this, X3 is this. I think we've seen those numbers one time before. So let's go straight to the computation. This is equal to, maybe I'll start up a little bit higher and just remind us: C1, f of x1, C2, f of x2, plus C3, f of x3. That's all we're doing. But C1 is listed right here. So we're going to get 0.5556. Oh, sorry, I left off the b minus a over 2. So this constant isn't part of the table. We need to remember this constant, 0.6. What the table is going to give us is this integral. Okay, so in brackets, 0.5556 times f of 0.6 times negative 0.7746 plus 0.7. Plus, we're still in the brackets, so I will put plus 0.8889, that's C2, times F 0.60, because that's our x2, plus 0.7. And the third one is 0.5556 f of 0.6 times 0.7746 plus 0.7. And then I would need the brackets there. So 6 of the numbers used in that came from this table, these 6 numbers right here. Okay, I simplified this in stages, but you could plug that into a calculator and get 0, it equals 0.8942. So that's the answer, that's the approximation of the integral using 3 points, basically, which means really 6 variables. The 3 points, x1, x2, x3, c1, c2, c3 are their weights. And just to show you what we would have got using more points. This was n equal 3 points. So if we use 1, 2, 3, or 4 points, the value we get, well, we know the 3 point was 0.8942. 1 point was 1.036. Not a very good approximation, but you're using just 1 point and 1 weight. 2 would get us to 0.9101. And 4 gets us to 0.8939. And out to 4 decimal places, I hate to put exact, but this is exact out to 4 decimal places. If we'd have done the 4 quadrature, the 4-point rule. So that's our complete example of using the Gaussian quadrature 3-point rule.